So now I'm the one between the break, so I will hopefully make it as entertaining as possible. And today I want to talk about a little bit about the HPC challenges for a standard platform vendor, as you can call Dell. And so this is interesting. It takes a while, because after all, people know us as a standard PC maker, right? We make standard servers using standard components, CPUs, memory, graphics cards, etc. But ultimately, we want to be better than our dear competition. So how do you make a difference? And also, if you want to make a difference, then you really need to dig deeper than only look at specification sheets. So one important observation is that in the old days, everything used to be proprietary. If you look at the old Crays and the old mainframes, then you had CPUs that were proprietary, you had memory that was proprietary, the operating system was self-developed, compilers, the whole middleware, even the disks had proprietary firmware on them. Then we came into the general purpose PC area with the rise of the Beowulf HPC clusters. And now we see, with the entrance of ARM and the Open Power Foundation and the EPI initiative in Europe, that we are starting to have more choice with regard to hardware. And this is a statement from the Vice President of Microsoft Cloud Solutions, who said, well, in this area, it is not only important to tune the software, but if you want to get the best performance, then you also need to tune the hardware. So you need to look at both again. So you can say, well, we are somewhat back to the old days again, because everything is cyclic anyway. Then we have seen quite a bit of disruption, and obviously this is Moore's law, as you see, with the starting in the 1970s all the way up to now. So performance has gone up, and at the same time the cost has gone down for per transistor. So you can say, well, this is what we call disruption. And even worse, if you look at the digital, or at least the companies who had digital in their names, then half of them have already disappeared since 2000. So there's a continuous change going on, and therefore also for Dell we still need to reinvent ourselves, you can say, to stay in the market. So when we talk about the market, then we see also changes that needs to happen, because we are hitting, apart from Moore's law, we are also hitting other ceilings. And we also have an enormous growth in the Internet of Things, right? So that we have a lot of endpoints that are communicating data. The data needs to be stored somewhere, so the data is that we created annually is exploding, and then also the business needs to do something with that data. So that's obviously AI and machine learning that then come into play. So when we talk about server layouts or architectures, then what we have seen is that the architecture trends are not keeping up. And this is a bit hard to read, but you see, for example, here in orange, that's the aggregate I/O memory bandwidth per core. You see that it is going down because the memory speed is progressing slower than Moore's law still is. The one in black here is the memory bandwidth versus the amount of instructions per core. That's also going down. So you can say a lot of things are actually going down. So I/O bandwidth per core is here. The memory latency is going up, so data becomes more expensive because it is further away, you can say. So we need to do something. This is also the reason why we are, for example, investing in new technologies like Gen Z, because we need an interconnect and a scalable system that can overcome barriers like this. So you see memory, that is the big problem, and that's why, for example, now CPU vendors are investing in more memory channels per core, because they have seen that for real application performance you need better memory bandwidth. So you can say, well, we cannot do much, right? Because we cannot up the frequency because there is what we call Ohm's law, so the voltage times the current. We have an upper limit over there. We cannot put more cores due to Moore's law. We know all the problems from Intel in the news with getting to 10 nanometer, for example. Software, well, that is a challenge because software is controlled by the users, and therefore that is the way to go forward. So you can say the focus is that we need to optimize for utilization, and we need to do something with the I/O problem. So that's also, for example, what Mellanox is doing with their sharp offload mechanisms, right? It is optimizing the I/O, basically. So this is what I already said. So network really is the problem. If you look at performance versus latency, and this is a slide from John McAlpin that he presented at Supercomputing in 2016, you see that everything is going worse if you look at performance, the calculation flops versus latency and bandwidth. Then we look at our standard HPC node because we also have issues there. The standard is 4 nodes in 2U, as we call it. This is our version, but everybody has one. Fujitsu has one, HPE has one, UOA has one, you name it. This is a 2-node system, and it has 4 nodes in it, and the nodes are sharing components like power supplies, fans, and the whole chassis, and therefore it makes it more reliable, and it also saves costs because you need less components. Now if you look at the this is typo, at the evolution of the dual socket, because we are now at our 4th model. So we started in 2010 with the 6100. Then back then we had Intel Nehalem CPUs and Intel Westmere. And you see low cores, high frequency, moderate power consumption per socket. We had 3 memory channels there per CPU. And as they are sharing power supplies, we could power all the 4 nodes in such a chassis with one 1400 watt power supply. And these were back then Intel list prices for what we call top of the line CPUs. So if we then go up to the chain, then you see in the latest version that we have far more cores, but the frequency has gone down quite a bit. But look at the power consumption per socket. It has more than doubled over these 7 years, but the form factor has stayed the same. So that is a challenge, as you can imagine. That's also the reason why we need liquid cooling, for example, because in the future this will even be higher, as we have been told. The memory channels has gone up slightly from 3 to 4, and now we are at 6, and I will come to that later. But we also need better power supplies because the CPUs have more than doubled the power consumption. And look at the prices. See, somebody has been making a lot of money on the CPUs, and it's not us. This is Intel list prices.
So price doesn't go down?
No, unfortunately for the top of the line it doesn't. And when I showed this to Intel, they said, you are cheating because this is what we call the E7 CPU, the enterprise. I said no, because it's still the same CPU. It doesn't have the enterprise features as before, so I still think that it's a valid comparison.
Yeah, it's like 7 times the number of cores and 7 times the cost.
So if you look at such a node, one of the 4, then you see 2 sockets, and you see that it has per socket it has 8 memory DIMMs or memory sockets. 6 in white and 1 is black, because this is already prepared for the 3D crosspoint that will hopefully come somewhere next year. But you see that we don't have much space anymore on the board. So 8 memory channels, yeah, we can do it, but then we have to sacrifice the NVDIMM or 3D crosspoint. So there's not much room. If you look at such a node, and we have them in two versions. Then we have the air-cooled version here, and we have the liquid-cooled version over here. And this is cables, and your power supplies are here. But you can see it is pretty full. So we cannot make this much more denser. We have a special version that is available for very big systems that can do 3 in a row instead of 2, but then we have to do something with the power supply. So then everything becomes 48 volt DC, and you have separate power supply units underneath the racks. If we go back to performance, then this is the famous Intel tick-tock, that where a tick is a new microarchitecture and a tock is then a die shrink or a manufacturing optimization of the same microarchitecture. And they have also been steadily increasing new capabilities for the chip. So you see, we started with SSE in 2007, then we got AVX in 2012, and now with the Intel Skylake, we are at AVX 512. So every 3 years, something new, you can say. But this is a challenge, because that means if you want to get better performance, then your application needs to make use of those new instructions, because otherwise you are not gaining much by buying new equipment. And if you look at the state of the HPC software, and I've here listed the 8 major verticals, you can say, from CFD to computational structure mechanics. That's mainly ISV codes, and all they care about is the accuracy of the solver. So they are very reluctant to introducing support for new instructions, because it might lead to different answer. So you see that most of them nowadays do support SSE2, but AVX, apart from I think LSDyna, very little support over there. For the open source kind of applications, it's better. So if you look at weather and molecular dynamics, for example, and molecular mechanics as well, definitely a yes. Chemistry using orbital methods is different, because it's not really suited to use factorized instructions, because the loops are too small. And oil and gas, it depends whether you're doing seismic processing, then I say no. If you are doing reservoir simulation, then it's yes. So you see, ISV support is poor, less of an issue for open source, but you have to make your hands dirty. So the CPU vendors are making it the problem of the developers to get better performance, which also hurts us, you can say. Now, what is Intel doing about all the new trends? So the decline of the memory bandwidth, the higher latency, etc. What they are doing is that they are introducing more tuning knobs. So you have more options to tune the hardware to the application. So if we take the Westmere of 2009 as our baseline, where we said, well, CPU bandwidth is okay between CPUs, memory bandwidth is okay, and we had high frequency. Then you can see sometimes due to a microarchitectural update, some things got better. So for example, at the Sandy Bridge, because of the introduction of the new PI link, better bandwidth. We also got an extra memory channels, and we got AVX. So this was a huge update. Then this was the die shrink. So you see, not much, but we got an extra snoop mode. So that is about snooping of remote cache lines. If you get something from memory, you load it in cache, you have to verify whether the other CPU on the same board also has that cache line in its memory, or in its cache. So you see that what's happening, you get more tuning knobs all the time, and you also get new capabilities. What happens with all the turbo modes that we now have for the different instructions, that we get performance variations, and this is also hurting us. What I'm showing here is a cluster of 256 nodes, and I have measured the link-back performance of the first socket here, so CPU 0, and HPL performance on the second socket, so CPU 1. And although you can see that, well, generally spoken, CPU 1 is better performing than CPU 0 because it gets more cold air due to the design, but you see that there's quite a variation, right? While you would have expected that it would all be here, you actually see that it can go up all the way from 320 or lower to 350, 360 gigaflops. So that is 10% of performance variation. And all the CPUs are identical. The reason for this is that you're using turbo mode.
Just a question.
Sure.
Does anyone have the data on the working temperature of each of the points?
Yes, they are more or less the same because
where's the peak?
because the inlet temperature is the same for all.
That's a big limitation.
And outlet also. That is what we verified. We also swapped low performing CPUs with a node of the high performing CPUs, and the performance went with the CPU. So it was on the CPU, and what you have is that some CPUs have the ability to better utilize their turbo than others, and that is due to manufacturing variations. So where you have been on the wafer actually matters whether you are able to get better turbo than others. Anyway, but this is a problem for us, as you can imagine. So what if we want to scale it up to a higher number of nodes? Then obviously we look at MPI. So if you look at InfiniBand in particular, but it could also be Omnipath, but just say high speed, low latency network. And I here have my two nodes. Right, here are my CPUs in sandwich time. I have my memory, it's NUMA. Here are my QPI links, and I have one network card. If I then transfer data, then it's just a copy. And actually that is still what we're doing right now, but we have far more cores. So you see, we had, let's say, 8-core nodes here, very common in those days. Now we have 20-core CPUs. So 40 cores per node, but we still have that same network card. And you can already see what is becoming the problem here. 60 cores, we had FDR, which was 56 gigabit per second and around 1.3 microseconds of point-to-point latency. Now we have 40 cores, EDR, 100 gigabits and less than a microsecond latency. The problem is, in a lot of codes, is that the performance is being killed by MPI all reduce. And this is what Richard showed as well in his talk, where he explained the sharp component, which can solve the problem, but then you need to have more than one switch domain. And what I'm showing here is that this is the wall clock time, and this is the MPI rank number. And then I am plotting the amount of time that it takes for the application, so the fraction of the wall clock time for the application here, and this is MPI time. So you see that there's not much of an imbalance. Here there's a lot of load imbalance, for example, because it is CFD, but in red you see the big MPI all reduce. And this is what I call the MPI all reduce disease, because a lot of applications are doing very small all reduces. So they just want to, for example, distribute a single value. So then it is a value, or it is a transfer of less than 64 bytes. And this really hurts in terms of OpenFOAM. This kills your performance. And this is another CFD app which is behaving somewhat better, but you still see a significant all reduce time, and even for molecular dynamics And for PAM crash, for example, you see there is a big all reduce, and 90% of them are very, very small. So very hard to optimize because it is such a small data. What now becomes important, if you look at the all reduce, where you are doing that between two nodes. So we had FDR, so we did do 32 transfers. If we say that you optimize first, where you reduce to one core and then you do it to the other. So much more messages. So what now becomes important is the message rate. And that's why we see, luckily, developments happening. So if we start with the Connect X3 FDR chip from Mellanox as our baseline, then we see that we got better bandwidth when we went to EDR with Connect X4 and later on Connect X5. So we got to 100 gigabit. We got better latency, although I see that my graph is actually wrong, but you see that this is improved. So the latency has improved. Higher is better for everything, but the major development has been in message rate. So I think that this will solve, hopefully together with what Mellanox is doing with the offload, this will solve scaling issues when we go to very large machines, because an all reduce or something like an I send, I receive, that we have been told that it's very good to do. So that you first post the receives, then the sends, and then you do something compute intensive, so you hide the latency, and then at the end you do the wait all, from textbook. This actually scales poorly if you have a lot of nodes, because MPI wait all just keep pulling the network for incoming messages. So this is killing your rate. So therefore it is better to do I send to do I receive and then a blocking send. That is better than to do the wait all, because that is hurting your message. So if you do it all properly, and this is an example for lamps that completely hides the network latency. What they do, you see they're doing send, I receive, and just a single wait or a wait any, so they don't do a wait all, and you see very little MPI overhead and very good performance to, I think this was 860 cores, so a lot that you can do. How much time do I have? A little bit more. Last thing that I want to show you is the efficiency of a Skylake CPU. This is what we get from Intel. If you look at the nice product offerings, and they say that this is the HPC workhorse. So it's the 6100 model, where you have 6 memory channels at the fastest speed. You have 2 or 3 UPI links, sorry, and you have the highest turbo boost, and you have 2 AVX 512 FMAs as well. But what about this one, where we have same channels but a little bit slower, we have less turbo headroom, and we have only 1 FMA, but it's far cheaper. So what I did do here is that I compared the 6126 with the 5118 that has same amount of cores but a little bit slower, just to see what it compares like. So again, we have less memory speed, 1 FMA, slower AVX 512 and less turbo. This is the speeds and feeds, right? And you see here, especially if you do AVX 512, then it can really hurt. But look, per CPU, list price, it is almost $500 cheaper. If you then look at the baseline where we do eStream Triad, you see that we are sacrificing a little bit of bandwidth because of the slower memory speed. And where we are really hurting is in link pack, because we only have one FMA instead of two. Then if we look at our Roofline for both CPUs, you can see that the peak for the 6126, so the gold one, is much higher than it is for the 5118. I did test a few apps, so I tested Chromax, I tested a CFD application which is memory intensive. Obviously I did do DGEM, and I tested FASP and also WRF. So different characteristics, different kernels, different loads. Then I need to measure performance, so I need to count flops and memory speed. So what I'm then doing is that I can use the performance monitoring unit of the CPU, which is special registers in the CPU that can measure all kinds of instruction types. And I can also, on the core of the CPU in gray, I can measure the memory load and stores. So I will skip this. What I did do was that I wrote a tool that can do it, and I just run the tool, and then I spawn the real applications, and then I get something like amount of cycles, cache usage. I can measure the frequency during the run because I know the amount of cycles and I know the walk clock time. And this is where it becomes interesting, because I can measure all the different floating point instructions being done during the run. So yeah, Chromax is a very good citizen, because this was for 75% or more using AVX 512 packed instructions, so factorized instructions. You see that it had very little memory bandwidth per node, so very high arithmetic intensity. So where are the flops? You can say, well, when we look at the floating point ratio of the application, so the amount of the floating point instructions compared to the total number of instructions, you might be surprised. Because most of the HPC applications, apart from, well, this was not an application, but it was 60% at most floating point, and for the others, less than 50%, or even far less than 50%. So much for your factorization capabilities. Well, DGEM obviously is 100%. So, how many gigaflops did we get out of our floating point? Well, if we know that the peak for a single CPU is this, well, we are exactly hitting the floating point peak for DGEM, but for the others, well, it was half of the peak at most, and for some it was even 50 or 40 gigaflops. Is something that you can do on a single core, you can say. So very insightful. If you then look at what you're getting, if you go from the 5 series silver to the gold one, then it depends a lot on the application. Remember, we had 10% faster clock, and we had around 10% faster memory. So you can see that for most, actually it is that 10%, or sometimes even more, but that is really it, except for when you do DGEM, because this is a flops model. So you see that it is not really much more. So therefore, if you are budget constrained, then the 5 series, and you are not doing a lot of flops, the 5 series can be very, very interesting. And if we then plot it in the Roofline model, and this is our peak, so this is where we want to be optimized. So on the right, because this is the memory bandwidth here, and this is the arithmetic intensity. You want to do a lot of arithmetic intensity for a good bandwidth. You can see stream and the CFD are totally memory bandwidth bound. They're here doing very little flops, and you see that WRF is already slightly better, but FASP and Chromax are, well, quite good. So you can say for these two, I would use the gold series. For the others, it is memory bandwidth bound. So use more memory channels or do something else. So summary is, HPC applications are less floating point intense than you might think, and sometimes the Gold 5 series can be a cost-effective alternative. And if you need the bandwidth and the flops, then go for the 6 series. So this is also the kind of studies that we are doing to find out what the best possible solution is for you. Thank you.